if on a quiz or test you wish to use this, you need to write it on the test or quiz. It is not accepted anywhere. The only people who potentially recognize it would be anyone who's had me as an instructor before, but other than that, it is not accepted anywhere. So you can write Newton seconds, kilogram meters per second, or define your own unit. And it doesn't you don't even have to use capital D. You could come up with something else. Doesn't even have to be a letter of the alphabet. So this is accurate as long as that's written down. All right, so what is the momentum of the 3 kilogram mass?
12 kilograms.
Negative?
Wait, oh, negative 12, yep.
Because the velocity is in the negative direction, negative 12. I'll just simplify it because I don't feel like writing the whole thing out. Now the fancy math. What is the total initial momentum of the system?
-2. Kilograms meters per second.
Yep, all right.
You said it was also Newton seconds?
Yes.
Okay. Is that because kilograms times mass, kilograms times meters is newtons?
No, a Newton is defined as a kilogram meter per second squared. And if you multiply both sides by seconds, you get rid of one of these, one shows up over here, so Newton seconds.
Okay. Gotcha.
So to get this final momentum, it's just like subtracting the two or like adding the two together?
I think you just went way complicated there. What is the final momentum?
Oh, wait,
-2.
It's the same thing,
right.
Okay.
We got the -2 from,
just adding.
yeah, okay.
Yeah, when I'm talking total here, it's just the sum, add them up. So my final momentum is the exact same as my initial momentum. And I did a test question years ago where I started out with what's the initial momentum, people had an answer. Second question, what's the final momentum? Way too many blanks, considering they just answered what the total initial was. All right, so let's talk about after the collision. They stick together. This is known as a perfectly inelastic collision. I'll talk about the naming system in a bit, but if you ever see perfectly inelastic collision, translate in your head to they stick together. So afterwards, I got a blob here of 8 kilograms with some velocity. What I want to know is how fast is this blob going? Well, I know what the total is. -2, and that's equal to mass times velocity, so that's equal to 8 times whatever that final velocity is. So my final velocity is -1/4 meters per second. Or for the decimal fans, -0.25. Recognize the power of this. Before they touch, the normal force, in this case, they're going to hit each other, they will exert a normal force on each other. So the normal force starts at 0. They're going to hit. And so the normal force is going to go from 0, it's going to spike up. So the force being applied to each other is not constant to start with. So if we try to use F equals ma, it becomes incredibly difficult because the force is not constant. But with the power of conservation of momentum, we don't need to know. All we need to know is what happens beforehand, and then we can figure out what happens afterwards. We are ignoring what's happening during the collision, or during the interaction, other than they will eventually reach some constant velocity in this particular case. Let's take a look at a slightly different final. So after. The 5 kilogram bounces back at 1 meter per second. The 3 kilogram V3 final. What is the velocity of the 3 kilogram mass after the collision? Again, I know what the total is. What is the momentum of the 5 kilogram mass after the collision?
1. -5.
-5.
Oh, sorry. That was, yeah.
I don't know what this is. It's easy enough to find out, but there's not enough information right at this point in order to find it. But we do have one other piece of information. I know that -2, my total, is going to be -5 plus P3 final. Therefore, what is the momentum of the 3 kilogram mass afterwards?
3.
And that's going to be equal to the mass, 3 kilograms, times its velocity. And therefore, the final velocity of the 3 kilogram mass, positive 1 meter per second. Questions?
We got that just by adding 5 to the other side?
Yes.
Okay. And then we got the velocity because we know the mass and we divided it by the momentum.
Divided momentum by the mass.
Oh, yeah.
So Descartes divided by kilograms is meters per second, and then 3/3. Math people tell me it's equal to 1. All right, so let's take a look at impulse. What is the impulse that was exerted on mass, on the 5 kilogram mass?
Well, it's the same as the momentum, right?
Not the way you worded it.
Oh, yeah.
Yes, okay. So what's the change in momentum of the 5 kilogram mass?
-15.
So the impulse on the 5 kilogram mass is final momentum minus initial momentum, which is -5 minus 10, or -15 Descartes, or Newton seconds, or kilogram meters per second. What is the impulse on the 3 kilogram mass?
15 as well? Positive 15.
3 minus negative 12. The total change in momentum is 0. So it makes sense that if one gets negative 15 units, the other one gets positive 15 units because the total change is 0. But this also brings up this idea of when is momentum conserved and when is it not. Because momentum was not conserved for the 5 kilogram mass. It went from 10 units to negative 5 units. This went from negative 12 to 3. So the total momentum was conserved, but for the individual parts, it was not conserved. And so we get introduced the idea of open and closed systems. Open system and closed system. Momentum is conserved in a closed system. In a closed system, you're taking into account everything. There are no objects, rewind. In a closed system, there are no external forces.
So, wouldn't that only exist in space though?
Yeah, well, no external net forces.
Okay. Net being,
Total.
okay.
So if I take a cart and I roll it along the table there, I don't have to worry about the force due to gravity because there's a force due to gravity down, normal force acting up. The net force is close enough to 0 that we don't have to worry about those kind of forces.
Okay, okay.
Our view closed system is we're finding the momentum of every object involved. But if I take this marker and I let go, and I look at the momentum of the marker, obviously there was some external influence on it. It did accelerate. So it's an open system if I look at just the marker, but if I look at the marker and Earth combination, well, now I've taken them all into account, unless I want to take air resistance into account. So usually it comes down to at what point is it good enough to call closed?
So the whole, like both of the boxes together, that's a closed system, but each individual one is an open system?
Yes. And so typically we look at, well, especially for collisions
The whole.
with objects. Yes.
Is it negative 15 or positive 15?
Here?
Yeah.
It should be positive because it went from negative 12 initially up to 3. And so the change in momentum was positive 15.
And why is it a negative 15?
Because it went from 10 to negative 5. So we start out with, so for the 5 kilogram mass.
I got it.
Okay.
That's for the first one, first box, and the other one is for the other box?
Yes, yes.
What should we write for an open system? Like momentum's just not conserved?
It's not conserved.
Yeah.
You'd have to be given more information to figure out what's going on.
So, like an example of a closed system would be, I mean, we just did one with 2 masses smacking together, but, well, I guess I should ask what an example of an open system would be then.
Well, besides marker falling, car skidding to a stop, any place where there's a change in momentum and we're not really considering where that momentum is going.
Okay, okay,
Or going or coming from.
yeah.
Sorry,
where did we find that the final momentum was 3?
Because I knew that the total, from conservation momentum, I knew that once I figured out my initial momentum, I found the final momentum. It's -2. I knew the momentum of this mass right here was -5, because mass times velocity. And so, -5 plus something is gonna get me -2 for my total.
Okay.
And so that's why this had to be 3. This is the math problem right here. Any questions right now? Any other questions? Keep that, let's see.
Alright, I hate to break your train of thought,
Yes.
but a closed system would have something acting on another thing, or the momentum, like transfers to like another object or something. Like if this was just being suspended and I dropped my pencil on it and the pencil stayed but the calculator fell, that's where a closed system is.
I would consider it a closed system. In that particular example, as it falls, are we worrying about the acceleration due to gravity?
No.
Then yes, that would be a closed system.
Okay.
Is an easier way to put it that a closed system, you consider both parts of the force, whereas in an open system, you're only considering one part of the force, since there's an equal and opposite for each one. For a closed
Yes,
system, you have
I
to
think
consider
that's
both,
fair to say, yes.
and then for an open system, you only consider one.
Okay.
Yep. All right. Let's connect this a little bit with what we've just done with energy. So all of you know the formula for kinetic energy, and I'm about to ask it so that you can all share with me. What is the formula for kinetic energy?
1/2
So let's figure out what the kinetic energy is of this object right here. K5 initial.
Four, 10?
I think it's 10. 10 what?
Meter, no. Yeah, newtons. No, is
Joules.
Joules.
it joules?
Newton meters would also have been acceptable, or kilogram meter squared per second squared. All right, so the kinetic energy initial of the 3 is
Wait, what is it?
6?
Oh,
Oh, no, wait, never mind.
forgot to square something.
24?
I think it's 24.
yeah, it's 16 times 1.5.
Mhm.
And so therefore, my total initial kinetic energy
Is this for the
It's just
system?
10
Is it
plus
34?
24, is that 34?
Yep. So we have 34 joules of kinetic energy to start with. Now let's come over here and see what K final is. So for the 5 kilogram mass,
It's just
2.5
2.5, yeah.
joules, yeah.
and for this one right here, the velocity is 1 meter per second, so the speed would be 1 meter per second.
So it's just 1.5.
All right, so we started out with 34 joules of energy, of kinetic energy, and we end up with 4 joules of kinetic energy. So obviously, there's energy lost on a macroscopic level. Realistically, where did that energy go?
Poof, into the air.
In what form? How would we know that?
You could hear it,
Like sound.
and it would create some amount of heat, I suppose.
Yeah, those are the 2 big things right there. You would hear it, and the objects themselves probably heat up a little bit. Now, this is all on, or in space, we're not dealing with any potential energy involved here because there's no conservative forces involved. So there's obviously energy lost in this particular case. We can start to narrow down or identify collisions based upon what happens with the kinetic energy. And so that gets into the naming system. So before I get into the naming system, because there's 3 different systems that I'm going to introduce you to, any questions?
Yeah. Sort of general though, in space, if the objects still collide, can you still lose energy to sound?
Oh, no, I'm trying to think if there's some bizarre exception, but no, I can't think of one right now.
So they would just heat up more than they would
Yeah.
in air?
Is that because sound waves?
They need a medium to travel through.
Yes.
So since there's no air in space, there can't be sound.
Oh, because it has to disrupt like molecules.
Yeah, it's just a
Okay.
concussive force through gas.
Okay.
So it sort of pushes.
Okay.
All right, so in a collision, so these are collisions. We'll call this naming convention number 1. So if the initial kinetic energy is equal to the final kinetic energy. Naming convention number 1, this is known as an elastic collision. Naming convention number 2, this is known as a perfectly elastic collision. The trouble is, I don't remember which textbook does which convention, so that's part of the reason I'm going through this.
So it's elastic or perfectly elastic? It doesn't matter.
Yeah,
Okay.
that,